Hello, everybody. My name is Eva Rivas Villanova, and I'm from Keysight EDA Product Management Team for System Design. I am delighted to be here and thank all of you for taking this moment to be with me to attend this webinar on 5G NTN physical layer simulation. We have about 30-35 minutes here, and I'd like to take you on a whirlwind tour through the 5G NTN landscape, including where we are today from a technology standpoint and how we got here. We will discuss some of the impacts being seen, felt, and experienced across the industry. Along with that, I'd like to do a little bit of level setting. Thanks again for being here with me, and with that, let's dive into it. I want to start by saying this. At Keysight, we believe that the world of communications is at the cusp of a technology-driven inflection point. Right this very moment. This shift isn't merely on the horizon. It's here unfolding in real time. The velocity of technological progress is accelerating at an unprecedented rate. As a society, we often find ourselves caught up in the ebb and flow of hype cycles, particularly in technologies. I'm sure everyone here can relate to that sentiment. However, when it comes to NTN communications, this isn't just another passing trend. It's tangible and significant. I acknowledge that reaching this point hasn't been an overnight journey. It's been a long time in the making. But now, here we stand at a transformative moment in communications, and it's unfolding before our eyes. Let's take a moment to outline our agenda for today's session. First, we will explore the main use cases of 5G NTN and the driving factors behind its adoption. Next, we'll explore the 3GPP 5G NTN standard. Following that, we'll transition to discussing the NTN transmission path modeling, reaching theory to practice. This segment will provide insights into how theoretical concepts are applied in real-world scenarios. And lastly, we'll showcase the Keysight integrated design environment, demonstrating its role in facilitating development and optimization of 5G NTN solutions. Let's unpack why there's suddenly a surge of interest in satellites. It's a matter of seizing the opportunity. Historically, achieving high-speed internet coverage on a global scale has been both costly and challenging. However, satellite technology presents a viable solution to this long-standing issue. Furthermore, traditional terrestrial infrastructure, such as cell towers and fiber optic cables, is susceptible to disruptions caused by natural disasters. In contrast, satellites offer a more resilient alternative, capable of maintaining connectivity even in adverse conditions. Furthermore, consumer preferences are evolving with features like denser coverage, emergency services, and enhanced messaging capabilities becoming crucial differentiators. This shift in consumer demand underscores the growing need for reliable satellite connectivity. Additionally, the significant reduction in satellite launch costs in recent years has fueled interest in ambitious projects, such as constellations with thousands of satellites. This cost-effectiveness has made previously unattainable endeavors feasible and financially viable. Lastly, advancements in satellite technology, particularly the use of low Earth orbits, have revolutionized the industry. By enabling lower latency and higher data rates, satellites have become increasingly attractive for a wide range of applications. Within the scope of application domains for 3GPP 5G NTN systems, we recognize the importance of two key areas: narrowband IoT NTN and wideband NA NTN. Direct satellite access for user terminals and cell phones extends beyond 5G NTN. Within the application domains for other NTN systems, we also identify two additional categories: proprietary non-3GPP and the modified 3GPP for legacy phones. Low Earth orbit constellations hold considerable appeal for handsets, primarily due to reduced path loss and improved link budget, which enhance signal quality and coverage, and lower latency and higher data rates, which facilitate faster and more responsive communication. However, deploying LEO constellations also presents challenges, including increased Doppler effect caused by swift movement of satellites and the need for a substantial number of satellites to maintain uninterrupted service coverage, which introduces logistical and operational hurdles. Success in transitioning from satellite to smartphone handsets relies on key factors: continued investment in new satellite constellations for broadband, development of low-cost terminals for mass market accessibility, leveraging low Earth orbits to enhance connectivity, standardizing radio access to avoid fragmentation, adopting 3GPP 5G NTN for scalability, addressing necessary 5G enhancements for competitive viability, and resolving regulatory approvals and global agreements as potential risks. A recent study conducted by Keysight, Defying Gravity, sheds light on the top technical challenges facing the satellite industry. Among the key findings, system-level modeling and simulation have been identified as the fourth most critical challenge, while accelerated development times emerge as a top trend in satellite technology. System modeling is one of the most effective ways to shorten development cycles by spending more time in simulation to identify design problems before building hardware prototypes. And I can tell you that it is not just hours and dollars that are being saved here. It's better decisions that are being made. It's higher productivity and collaboration that is being experienced, more effective systems that are being designed, and in highly regulated industries, is missions that are being supported better. I want to ask everybody on the line today, is your organization prepared to leverage system-level modeling and simulation capabilities for NTN communications? Are you already experiencing the impact? No matter what stage of the journey you're at, we are here to help, including if you haven't started yet. Today is a great day to begin. So hopefully this sets the scene. But I want to dig in and give you an overview of the technology itself and how we came to this point. Moving on to the second point on the agenda. So looking at this timeline, we can see an overview of the history of 5G. Again, it may seem like a new era, but honestly, this was a long time coming. There have been loads of milestones along the way that have brought us to this inflection point that we see today. So we head in the time machine here, and we head back into the 2010s, when researchers and industry experts began exploring the potential of non-terrestrial network solutions. Fast forward into the 2020s, and 5G non-terrestrial network functionality is first standardized in 3GPP Release 17. The development and deployment of 5G NTN continue to evolve as technology advances and regulatory frameworks adapt, gaining momentum as we move into 2024 and beyond. So, bottom line, 5G NTN has come a long way since its inception and continues to evolve. If we look at satellite orbit with 5G NTN, we are looking at LEO satellites right now, and they differ from the traditional GEO satellites. LEO satellites introduce new challenges related to Doppler shift and signal delay due to the rapid movement relative to Earth. Initially, the traditional 5G channel model outlined in 3GPP Technical Report 38.901 primarily addressed stationary terrestrial links, accounting for factors like path loss and multipath propagation in Earth-based scenarios. However, as 5G technology advanced, it became clear that conventional models were inadequate for capturing the complexities of non-terrestrial networks, including satellite communication, high-altitude platform systems, and air-to-ground networks. To meet these unique requirements of NTN, 3GPP introduced Technical Report 38.811, offering comprehensive guidelines for modeling wireless channels across terrestrial and non-terrestrial link, ensuring accurate representation of the diverse scenarios encountered in NTN deployments. 3GPP has laid out two architectures, transparent, also called bandpipe, and generative. The transparent architecture for 5G NTN involves connectivity via a satellite acting as a repeater. In this setup, the ground-based GenOB communicates with the satellite, which then relays signals to and from user equipment on the ground. This architecture aims to maintain transparency in signal propagation, where the satellite acts as a relay without significant processing or modification of the transmitted data. The generative architecture, on the other hand, involves more active processing by the satellite. In this case, the satellite acts as a base station, not just a repeater. The GenOB communicates directly with the satellite, which processes and generates the signals before transmitting them to the UEs. This approach allows for more efficient signal management and optimization. Moving on, let's look at end-to-end transmission path modeling. In satellite link transmission, the RF characteristics differ significantly from terrestrial, manifesting in greater path loss, extended delays, and increased frequency errors. Transparent or bandpipe requires modeling satellite hardware as part of the wireless link. And in addition, interference and other environments must be considered when validating the link. The end-to-end RF link can be divided into several subsystems, each contributing to the link's overall performance. RF channels experience not only satellite channel effects, but also terrestrial fading, necessitating comprehensive analysis and mitigation strategies. The satellite payload comprises various components, such as filters, power amplifiers, and mixing circuitry, each introducing its own set of challenges, including phase noise, thermal noise, and distortion. At both the transmitting and receiving ends, thermal and phase noise characteristics are added to the signal. Multi-domain modeling is essential, covering analog RF, digital, and baseband DSP to accurately capture the system. System designers partition the link budget and optimize performance parameters such as power, efficiency, linearity in the transmit chain, and noise gain and linearity in the receive chain. This ensures a balance between various trade-offs to achieve optimal system performance. A key aspect is antenna modeling, because with LEO satellite links operating at higher data rates and frequencies, there's a growing need for antennas with increased gain and power transmission capabilities. We can understand this just by looking at the free space path loss equation, where loss increases with distance and frequency. As a consequence, traditional fixed illumination antennas in large GEO satellites are transitioning towards reconfigurable multi-beam phased arrays in LEO satellites, enabling precise point illumination and adaptive coverage. Beam steering and beamforming capabilities are essential features in these phased arrays, allowing for dynamic adjustment of beam direction and shape to optimize signal coverage and quality. It's important to recognize that the electromagnetic spectrum is a finite natural resource. Phased arrays, akin to advancements seen in 5G and anticipated in 6G, represent technological solutions aimed at maximizing the efficient utilization of the spectrum resources, ensuring optimal performance and sustainability in satellite communication systems. Higher power transmission also means that power amplifier designers are tasked with developing highly efficient devices that must also be highly linear and capable of handling the complex modulation schemes employed for high data rates. To address these challenges, power amplifier designers need simulation tools that can model linearization techniques such as digital pre-distortion, DPD, which has become increasingly popular. Accurate distortion modeling is key, both in-band and out-of-band. Lastly, satellite link designs need to be validated with 5G signals and appropriate channel models. System engineers, RF engineers, and antenna designers need flexible 5G source configuration for different NTN deployments, as well as TR38.811 compliant channel model implementation, which captures both satellite and terrestrial components of the link. Let's see how System Design SystemVue helps deploy low Earth orbit satellite-based 5G system. How can we use system design in satellite and cellular convergence? Our objective is to send data bits from the 5G base station to the user equipment via this satellite. Using a gateway, the base station will transmit modulated data in S-band to the satellite, operating within a band pipe architecture. So the satellite's job is to relay information, acting like a mirror, receiving the signal from the gateway and transmitting it into a different frequency to the UE on it. At the UE, we will demodulate the signal and look at signal quality. First, I will talk about aspects of link budget that hopefully are useful to you. Then I will talk about system design and its NTN channel model and how they work together. And lastly, I will show a complete end-to-end simulation for bandwidth 5G NTN system, aiming for that coveted digital twin. And one of the nice things about this demonstration is the implementation of phased arrays for the satellites receiving and transmitting antennas. To begin with, let's examine power electronics and conduct a link budget analysis. I'd like to start by exploring some of the approaches frequently adopted by customers. We are confident that we have a superior approach, yet we acknowledge that many system architects still begin here: spreadsheets. Homegrown tools pose challenges from management and design perspectives. They require extensive engineering hours for customization with each project. They lack scalability across projects and are prone to data entry and modeling errors, as well as having limitations in handling non-anticipated impairments. Now our solution: Spectrosys, the broadband frequency domain RF system analysis in system design. We have color-coded the measurements here. Coral represents the base station and gateway. Cyan denotes the satellite, and purple corresponds the UE. Here we showcase the measurements alongside the design in a format that's intuitive to you, your management, and hopefully even your customer. If parameters like estimated DVM hold significance for your customer, you can conveniently track it through the system, along with calculating other parameters like antenna EIRP or antenna G/T, a feature that antenna specialists will find invaluable. What's more, all these measurements are easily selectable and trackable because Spectrosys analysis automatically keeps track of them. So it's simply a matter of choosing which data you want to present along with your design schematic. For those familiar with Spectrosys, it's worth noting that all these components are subnetworks. Only the source and oscillators are found in our library. One of these subnetworks is actually the LEO RF engineering design. In our integrated design environment, I have the flexibility to incorporate elements such as my antenna. This means I can factor in antenna gain and engage in beamforming design and analyze phased array. Take, for example, this hexagonal array I've designed for my satellite transmitting antenna. What's particularly advantageous is that our phased array analysis has undergone validation by numerous customers from aerospace, defense, and wireless industry. Try doing that with your spreadsheet. Another feature we offer is the ability to visualize measurements using budget plots, or as we refer to them in Spectrasys, level plots. I always draw attention to the x-axis, which I've kept at the subnetwork level for clarity in this demonstration, where you have the parts lineup. You'll notice that you can track your measurements along the designated system path. The one I'm highlighting here is TCP, which represents desired channel power. As we progress from ground to satellite, you will observe the path loss and efforts made within the satellite to compensate for signal loss, only to experience another drop as the signal travels from the satellite to the UE. Through Spectrasys simulations, I can perform design exploration, identify red flags in my design, and then mitigate them. Budget measurements can also be presented in tabular form. Here, I look at the gain and DCP values to determine the gain and EIRP for the satellite TX antenna, essential for link closure. With this data, I can proceed with beamforming. In this scenario, I explore two potential designs, a 6x6 rectangular array and a 37-element octagonal array. Phased array analysis reveals that the hexagonal array achieves superior directivity and lower side lobes. The rectangular array offers a simpler construction process but lesser performance. I revisit the budget analysis to evaluate the gain and EIRP for the satellite RX antenna required for link closure. Using this information, I proceed to explore beamforming techniques, focusing on a 4x4 rectangular array. And I see that the rectangular array with custom taper exhibits heightened directivity and minimized side lobes compared to the untapered 4x4 array. The integration of phased array analysis and Spectrasys into one platform streamlines and shortens design throughput, so critical to users. Simulation data allows me to make informed decisions. A significant challenge is also the LEO power amplifier, which must deliver sufficient power to transmit signals. For the power amplifier designers tasked with creating highly efficient devices for LEO transmitter links, we integrate a tool called DPD Explorer into ADS. These amplifiers must have high linearity to handle the 5G signals for achieving high data rates, which can have significant peak-to-average power ratios. With this tool, designed specifically for the ADS circuit designer, you can discover power amplifier performance metrics such as ACPR and EVN after DPD at an unprecedented speed and fidelity. Leveraging the same measurement algorithms as in the PNAX, it eliminates discrepancies between simulation and hardware. DPD Explorer is differentiated by the novel dynamic gain model, which addresses nonlinear memory effects in broadband topologies like GAN, TORTI amplifiers. Transitioning to data flow, our time domain analysis platform, we employ our 3GPP compliant 5G NTN channel model to simulate both feeder and service link. For a comprehensive digital twin, we require a flexible 3GPP compliant 5G source along with corresponding receiver. In my demonstration, I use a 20 MHz wide 5G NR signal operating at a carrier frequency of 2007 MHz, adhering to the 5G NR FR1 band specification, with a subcarrier spacing of 15 kHz and 106 resource blocks. Conceptualized as our digital engineering flow, system design data flow is where everything integrates. In this specific case, RF engineering designs from Spectrasys, RF phased array designs, wireless libraries, the 5G NTN channel model, and links to Keysight VSA software for measurements. The 5G channel model aligns with 3GPP standards for non-terrestrial networks, which involve using spaceborne or airborne vehicles as relay nodes or base stations. This model aims to faithfully simulate the wireless channel between the platform and UE or the gateway, enabling realistic assessments and validations of NTN communication systems. Now let's look into its key features. Firstly, it has a flexible trajectory definition capability. This allows us to accommodate various trajectory files, including those from SDK software and PropSim emulator box. The trajectory visualization with playback functionality provides dynamic measurements of the NTN link. We have the flexibility to configure antennas according to our needs, like for instance, multi-beam face-to-face. We want to emphasize that our 5G NTN channel model directly integrates into existing workflows. It's capable of reading SDK trajectory files, ensuring a smooth transition from SDK workflows. Additionally, it can share trajectory files with Keysight PropSim, offering a seamless path to emulation, another leap forward for engineering productivity. The scenario selection option lets me choose various scenarios to model different environments, including dense urban, suburban, rural, and user-defined. I can also select the common TDL and CDL terrestrial model. The satellite link only option disables terrestrial modeling, focusing on the satellite link, which models also Faraday rotation to validate antenna polarization. The ionosphere contains free electrons due to ionization by solar radiation. Circularly polarized waves are inherently rotationally invariant. This means the polarization state remains unchanged, even after passing through a medium with Faraday rotation. In contrast, linearly polarized waves experience rotation, altering their polarization angle. For the end-to-end band type case, we will need two 5G NTN channel instances, one to model the feeder channel and another one to model the service link. And for a full digital twin, we need a flexible 5G source, 3GPP compliant, and a corresponding receiver. In my end-to-end 5G NTN simulation, I initiate the process by sending bits to my 5G NR source. The signal undergoes up conversion to 2.007 GHz frequency at the gateway, then travels through the feeder channel model to reach the satellite, where it undergoes translation to a different frequency, 2.117 GHz, before being relayed back to Earth through the service channel. Upon reception at the UE, digital signal processing techniques are applied to compensate for Doppler shifts and delays, including time drifting, and the compensated signal is then demodulated. In this setup, I utilize the VSA software receiver. We can see that the constellation has degraded at the receiver, as have EVM and power per resource element. With system design capabilities, I can effortlessly validate my designs across different non-terrestrial network conditions and 5G configurations. This greatly simplifies the process of estimating link margins for 5G SATCOM links. Start selecting the frequency band for your project and specific region, which leads to different atmospheric absorption and propagation characteristics. Then look at the power through the transponder and UE receiver sensibility and adjust transmit power based on link conditions and minimizing interference, keeping in mind that standard link margin values are different from one application to another. Backhauling, maritime, aero. One critical metric for many of our customers is the throughput versus the 5G signal modulation and coding scheme. The higher the modulation density, the higher the probability of receiving erroneous bits. In this example, we evaluate throughput for the CDLA case in an NTN channel, employing the receiver block from our 5G library along with the NR throughput sync. we increase the density of the modulation in our 5G NR signal until we begin to see errors, in this case with MCS set to 5. Users often perform these evaluations using different antennas, sometimes integrating their measured antenna patterns or from EM tools. Our 5G NTN channel model can directly import these antenna patterns, streamlining the process and enhancing efficiency. Lastly, validating designs in the presence of interferers provides insights into potential performance bottlenecks and areas of optimization. Incorporating interference in system design is straightforward. You can add as many signals as you want to a design. In conclusion, Keysight System Design tackles critical challenges, including the demand for virtual analysis tools for 5G NTN scenarios, the need for accelerated design of high-fidelity array systems, and the unmet need for broadband power amplifier validation with digital pre-distortion. As you've seen, the product vision is to reduce time to value for the designer. Anything they can do to streamline just improves turnaround and helps hit that market window. I hope at this point you're asking yourselves, great, how do I get started with this? We've talked about the what, we've talked about the how, and here's a bit about where to begin. System design, SystemVue, is a powerful tool that brings together RF engineers, phased array designers, and DSP developers to work harmoniously within a single environment. There are loads of great resources on our web. I encourage you to check those out. Leverage system-level modeling and simulation capabilities for 5G NTN communications and experience the impacts. This moment in satellite and cellular convergence really is monumental. Everyone on the other end of this webinar has to be able to understand the implications and embrace the opportunities that lie ahead. And with that, I want to wish you all the best in your 5G NTN journey. Thanks for your time today, and I hope the rest of your day goes well.